Hello. Here we have a classic projectile motion problem. We don't really have time, nor is this the venue for a full lecture on the physics of projectile motion, so I will work through pretty straightforwardly with the concepts in mathematics that you would learn during a projectile motion unit in introductory physics. So we have a football player. Football player kicks a football at a certain angle at a certain speed. You'll notice here that I've changed that word velocity to speed for reasons which will become clear soon. I claim that, in fact, that 15 meters per second, that is not a velocity as I tend to define it, but rather speed. And we're asked to find three quantities. Time of flight, that is how much time from the moment the football was kicked to the moment it hit the ground again. We want to know how far the projectile, the football, moved along the ground before it hit the ground. And we also want to know the maximum height of the football. And let's work through this in the way that we do as physicists, which is by visualizing it. We want to draw a figure which will help us put ideas together. We don't want to just go out and start looking through your formula sheets for formulas that seem relevant and then plug values in. That's a path to disaster. Let's visualize what's actually happening here and see if we can't use that to make these concepts make sense. So the football, like all projectile motion without air resistance and constant gravitational force, travels along a parabolic path. According to the text of the problem, there's no initial height to the football, so it seems that the football is starting on the ground and it ends back up on the ground, and the ground is level the whole way. I haven't drawn it quite perfectly because that's difficult to draw perfect parabolas in freehand, but what we do know is that parabolas are symmetrical. And for a projectile motion problem like this, the maximum height of the projectile, right here, I'll call that y max. That maximum height is exactly halfway along the path of the football here. The football starts over on the left here with an initial velocity of 15 meters per second at 30 degrees above the horizon. Velocity is a vector quantity that requires two values, a direction and a speed. So we would say that our speed, v naught, is 15 meters per second, and our angle, our kickoff angle, theta, is 30 degrees. And 15 meters per second at 30 degrees is our velocity. Our speed is just 15 meters per second. And this quantity is going to become important very shortly. So we also want to know our maximum x value here. We'll call that x max. And all of this is to say that we have we set up our coordinate system with positive y pointing in that direction up and positive x pointing in the direction along the ground in which the football moves. So let's think about this for a second. The parabola is symmetrical. It takes the same amount of time to reach the top, this point right here, the top of flight. And we also know, therefore, that it takes us the same amount of time to go from the top of flight back to the ground. So halfway through the total time of flight, that's when our height is at a maximum here. So we can say that the top of flight, and the ball is at its top point here. Let's call that time t1. We don't know what it is, but we're going to assign the variable t1. And what are our kinematic equations that relate time and something about the football when it gets to the top there? What do we know about a football moving through the air, reaching the top of its flight? Well, you'll notice that before the football reaches the top of its flight, the football is moving higher. And after the football reaches the top of the flight, the football is moving lower. That's the definition of top. What this means is, at the exact moment when the football is at the top of its flight, it's y max, halfway through the total time of flight, at that moment, the y component of the football's velocity is 0. For a brief moment, the football is moving neither up nor down. the vertical component of that football's velocity is 0. So we can say that v1 y is equal to 0 meters per second. The y component of the ball's velocity at t1, at time 1, is 0. And this is the crucial bit that will let us solve part of this problem. Now, again, this is not quite the venue to talk about the basic properties of vectors, but we do know that in 2 dimensions, vectors have 2 components. And according to this coordinate system, that velocity of the ball has a y component that points in the vertical direction and an x component that points in the horizontal direction. And by examining some of our kinematic equations, we can say that, well, our velocity at any given moment is equal to its initial velocity in that direction plus acceleration times time in that direction. So you might see on your formula sheet that you have something to the effect of your velocity at any given moment in time is equal to your initial velocity plus acceleration times time. This is valid for constant acceleration. And in our y direction, this is how we would change these variables here to make them useful for solutions. We know that our y component for velocity at some given time, initial velocity, and acceleration in that direction, that equation holds true for both the x and the y directions. And if we're interested in time 1, then we're looking at v1y. And by reasoning about how projectile motion works, we know that at time 1, at t1, by definition, by the way this problem is constructed, we know that the y component of that ball's velocity is 0. So v1y at t1 is equal to 0 meters per second. Now, doing a little bit of rearrangement, we can say that the y component of acceleration times t1 is equal to 0 meters per second minus v naught y. Well, that's easy enough. 0 minus v naught y is just negative v naught y, the y component of our initial velocity here. Now, we know that for projectile motion, again, for reasons which we are not able to cover during this brief time, we know that the y component of our acceleration is negative g, g being the gravitational constant, times time 1 is equal to v naught y. I'll label this all as a right here. The 2 negative signs will cancel out, and we get that our t1 is equal to v naught y over g. Now, doing a little bit of trigonometry right here, recognizing that our coordinate system sets a right angle between the x and the y components here, we can say that our v naught, the y component of our initial velocity, is v naught sine theta. And the x component of our initial velocity, v naught x, is equal to v naught cosine theta. So v naught y is v naught sine theta. Let's just go ahead and plug that in. V naught sine theta over g. Now, let's think about this for a second. T1 is the time it takes for the ball to go from the start to the top of its flight. The total time of flight is twice that, the time from the start to the top of flight, and then the same amount of time from the top of flight back to the ground. So the time of flight, we'll call that, TF, is equal to twice times T1. So that's going to be 2 V naught sine theta over G. And now we actually have everything we need to do to solve this problem. 2, our initial speed is 15 meters per second. Sine of our initial angle is 30 degrees. And G, the value of Earth's gravitational constant, is 9.81 meters per second squared. Now, again, we don't have quite time to go over this right now, the specifics of physics and the manipulation of units in algebraic expressions like this. But if you plug these values now into your calculator, you will get 2 times 15 times sine of 30 degrees divided by 9.81. That's the number that you plug into your calculator, times the units here, which we've got meters per second, no units for 30 degrees, divided by meters per second squared. Now, this first part, just the numbers, you can plug into your calculator. Your angle is given in degrees, so make sure that your mode is set to degrees for this calculation. 2 times 15 times the sine of 30 divided by 9.81. That is 1.529. The number is 1.529. 1.529. And then the unit is something that you have to do yourself by hand. Meters per second divided by meters per second squared. Well, the meters cancel out, and one of these per seconds cancel out another one of those per seconds. So we end up with 1 over a second, with the inverse of a second, which is simply a second. We were asked for a time, and we found a number of seconds. So that suggests that at least our calculations were dimensionally correct. And thinking about things, 15 meters per second, that's a reasonable kick speed for a football. 1.529 seconds, that's 30 degrees is pretty shallow. I've drawn this as an obtuse angle, but it should be an acute angle. 30 degrees is pretty shallow, so I think that's a reasonable time to visualize a football flying. So that's part A. Now, this is the key to everything. We have all of the information that we need to find the other two projectile motion issues here just fine. This time, the total time of flight is 1.529 seconds. So TF, total time of flight, TF is 1.529 seconds. And then T1, that's the time at which the ball is at its maximum height, is half of the total time of flight. So let's just calculate that real quick. 0.765 seconds. And I'll keep those values here because they will be useful for the other two parts of this problem. If this were an interactive lecture, I would have asked if there are any questions so far. Now, what we'll do next, usually you can take as a hint when you're doing these sorts of problems at this level, is that the A, B, and C, the different parts of the problem, of the physics problem, are set up in a way that helps you. So on your try solving each of those parts of the question in the order that they are given to you. You'll usually find that that helps you, that is a logical way to work through this physics problem. Okay, now we'll do part B. How far horizontally does the ball land? Well, that's easy enough. The projectile motion without air resistance, there is no gravity force that acts in the horizontal direction. Gravity, the force of gravity, the gravitational acceleration and therefore caused, doesn't affect the horizontal velocity of the ball, the horizontal component of the velocity of the ball. We can say that the V naught x is equal to, well, V naught cosine theta. V naught is 15 meters per second. V naught cosine theta. That's 15 meters per second times the cosine of 30. 15 cosine 30. 12.99, so 13 meters per second. And that tells you everything you need to know about the horizontal motion of the ball. The ball starts off moving at 13 meters per second in the x direction, it ends up moving 13 meters per second in the x direction. And at every moment in between, the ball is always moving 13 meters per second in the x direction. So simply, if you want to find the total x motion of the ball, you take the x component of the velocity of the ball, which is the same for the whole time, times the total time that the ball is in flight. So our x max, in this case, is equal to our x speed, which is v naught x, 13 meters per second, times our total time of flight, tf. That is tf, not ft. So 13 meters per second, and our total time of flight is 1.529 seconds. 13 times 1.529, that is 19.877 is the number, and then meters per second times second, well, the seconds cancel out there. So 19.877 meters. Again, we were asked for a distance, how far horizontally does the ball move, and we found an answer with units of meters. That suggests that our analysis was at least dimensionally correct. And finally, part C, how high does the ball reach? Well, we can't do the same procedure that we did for part B, because we know that, in fact, the ball is accelerating vertically, meaning that the y component of its velocity is changing with respect to time. You can't just do v naught y times t1. That is not going to give you the right amount of time. But what we can do is we can then use the other kinematic equation, the kinematic equation for motion under acceleration. We can say that your y velocity at any given moment in time is equal to your initial y value, your initial y position, plus v naught y times time, plus 1/2 times a y t squared. Now this is true for any y and any t, but we're actually specifically looking for our y max. And we know that our y max happens at time 1, which we have here. And now we can start plugging in some values here. We know that our initial y position is 0 meters, because the ball starts at the ground. We're defining that to be 0 meters. Our initial y component of velocity points up, so it's a positive value. So that is, equals v naught sine theta t1, and then 1/2, we know that our y component of acceleration under this projectile motion is negative g. The acceleration points downward. At every moment, the velocity of the ball is getting more downward. And we'll do that t1 squared. And now finally, we actually have everything that we need to do to plug this in. 15 meters per second is v naught times sine of 30 degrees times t1, which we calculated earlier as 0.765 seconds. And then this minus sign comes out in front, minus 1/2 times 9.81 meters per second squared, times, again, our t1, our time till the top of flight, 0.765 seconds squared. And if you'll permit me, I will do this calculation myself on my calculator. I'm running out of whiteboard space right here. So 15 times the sine of 30 degrees times 0.765 minus 1/2 times 9.81 times 0.765 squared. And that gives us a maximum height of 2.867 meters. Again, when we work through the units, we find that they end up in terms of meters, and that should yield everything you need to do for this problem. Once you get in the habit of doing projectile motion problems, you don't need to do all of this elaborate setup. You can recognize first you need to solve for the time, then you need to solve for the X and Y motion. You're also not trying to teach someone else to do this as you're doing it yourself. It took me 20 minutes to do this problem, but if I hadn't been narrating and writing things out as carefully as I had been, these are the sorts of problems that you can do in just a couple of minutes yourself. My name is Scott Douglas at scottteachesscience.com. And I really hope to talk to y'all at some point in the future.